We present our work on safe, large-scale, robust, nonlinear MPC in milliseconds via reachability-constrained system-level synthesis on the GPU. We consider controlling a robotic system with uncertain, nonlinear dynamics subject to bounded disturbances. On the left, the system operates without a robust policy. As disturbances propagate, the system drifts away from its nominal trajectory and ultimately fails. On the right, we apply a robust policy that explicitly accounts for these disturbances, allowing the system to remain safe. Given an uncertain nonlinear system, our method first applies sequential quadratic programming, linearizing the system and producing a constrained quadratic program. To solve this QP, we use our GPU alternating direction method of multiplier solver that recovers the solution in logarithmic time through parallel associative scans. We next synthesize a robust controller via system-level synthesis, again using parallel associative scans to efficiently recover the policy. Using this policy, we compute updated constraint tightenings that conservatively bound the effect of uncertainty, yielding an over-approximation of the original constraints that is enforced in the next QP. Through this iterative process, we recover a nominal trajectory and disturbance feedback policy that guarantees safety. We benchmark our formulation on a 10-link pendulum stabilization task subject to random pushes. Due to the logarithmic scaling of our method, we demonstrate significant acceleration in solve times, achieving a speedup of upwards of 97% compared to sequential CPU solvers, OSQP, and HPIPM. We also outperform comparable GPU augmented Lagrangian methods by 70%. On the right, we demonstrate the scalability of our formulation as the problem size grows, solving problems with horizons of 3,000 and 75 per state decision variables in 73 milliseconds, demonstrating the logarithmic scaling in all horizon, state, and control dimensions. We now demonstrate both the safety and the speed of our GPU SLS formulation. On a Dubin's car benchmark, our method outperforms learning-based reachability approaches, achieving 100% empirical safety while retaining the formal guarantees provided by SLS. Our solution, which is implemented in JAX, requires a one-time compilation time of 16 seconds, but after compilation, the online compute time is 47 milliseconds on average. In contrast, the learning-based baseline, DeepReach, achieves only 81% empirical safety despite 10 hours of training time. We also evaluate computational performance, comparing GPU SLS against the CPU-based fast SLS solver on the same task. For large-scale problems, our approach achieves up to a 237 times speedup, highlighting the logarithmic time scaling of our method for the robust policy generation. We also demonstrate that our method scales to large-scale navigation problems with a large number of constraints. In this experiment, our method successfully computes a robust policy for a Dubin's car in an environment containing 40 obstacles, navigating over a time horizon of 10 seconds. This demonstrates that GPU SLS can reason in an uncertainty-aware fashion within large, densely cluttered environments over long time horizons, something that is typically computationally infeasible for robust control methods. We further validate our method on control of a whole-body humanoid with 75 state dimensions and 19 controls. The humanoid is tasked with robustly navigating around an obstacle subject to an adversarial disturbance that pushes it towards collision. In the first two animations, the robot successfully avoids the obstacle, remaining within the robust state tubes generated by our method. We further illustrate this robustness by overlaying the robust tubes with multiple rollout trajectories under different adversarial disturbances, showing that all executions remain safe. For real-time deployment, we adopt a real-time iteration MPC scheme. At each control step, we perform a single linearization of the SLS system, solve the resulting problem, and roll out the updated trajectory. Using GPU SLS within this RTI framework, we robustly satisfy constraints online with an average solve time of 27 milliseconds. On the left, we show the humanoid navigating through two obstacles in real time. On the right, we visualize the corresponding planned trajectories with the robust tubes. We demonstrate the practical capabilities of our method on real hardware. In this experiment, our Unitree Go 2 EDU quadruped navigates around two obstacles using the nominal controller running at 50 Hz, with an average solve time of 18 milliseconds. Throughout the experiment, The robot successfully avoids the obstacles without violating any constraints, demonstrating that our method is both safe and capable of real-time operation. We also demonstrate our RTI GPU SLS framework on hardware. In this experiment, our Unitree Go 2 quadruped navigates around an obstacle under bounded disturbances. With our framework, the quadruped is able to jointly optimize the forward reachable tubes and nominal trajectory, all while remaining real-time. We conclude with a summary of our work. Thank you for your attention.